Hello everyone, welcome back to BC Calculus. We're starting lesson 40 today, which is in vectors. And I want to talk about, first of all, the notation for a vector. There's two ways that you actually can write a vector in this class. The first way looks like a coordinate point, but instead of parentheses, we have these little bracket looking things. This talks about the magnitude and the direction of our vector. And the second way is writing a vector in terms of coordinates of I, j, and even k. So we're going to actually do our vectors in two different ways with these problems. And they are pretty straightforward. So this is probably one of the easier lessons for us to show you. So let's go ahead and look at example number 1. It says, let u be the vector with the initial point 2, comma, negative 5. So we're at the point 2, negative 5. So at 2, negative 5, we're here. And then we have a terminal point at negative 1, 3. So negative 1, 3, which would be up here. And so we have a vector that looks something like this. And so we want to figure out what this vector is. Well, we can just say that it starts initially at 2 and it goes to negative 1. So this is very similar to geometry, where we're going to write the vector in the form like this, which is going to be our x comma y. And this is a translation. This basically means how do we move? So we start at 2, we start at x equals 2, or let's go around here. We start at x equals 2, and then we actually moved over to x equals negative 1. So we moved 3 units in the negative direction. So our vector u can be represented as negative 3, because again, it's just a translation. And then what do we do with the y? Well, we started at negative 5, and then we went all the way up to positive 3. So we went up 8 in the positive direction. So this is how we represent u in terms of this notation. We could also do it in terms of writing it as negative 3i, the little bracket thing, little arrow, plus 8j. And so we could do it like this as well. And these both are good representations of the direction of what this is. So in the units of I and then in j. And then it says, given that that's our u, and then v is already given to us as our notation, so we know that this is going to be 2 comma negative 1. And so again, it doesn't matter which way you guys want to write it. It's all fine either way. And so it says, we've already found the vector for u, but let's go ahead and find the 2u minus 3v. Well, it's exactly what you think we would do here. We would take 2, and we're going to multiply vector u, which is going to be negative 3, 8. And we're going to do minus 3, and then we're going to go ahead and do 2, negative 1. And it's very similar to like distributing. And we're not really distributing because this is just telling us that we're extending it twice. So our vector is actually going twice the length. That's really what this is. It's not that we're actually distributing it, but the math part of it really is that we're just distributing this. So we're going to end up doing negative 6 comma 16. So this lesson is not really about vectors. It's just how to do them simplistically. So again, this would be v. We would extend this 3 in the negative direction. So we would get negative 6, 16 minus 6, negative 3. And then again, we would say negative 6 minus 6 would be negative 12. And then 16 minus negative 3 would be 19. So our answer would be negative 12, 19. So this right here would give us a transformation of x negative 12 and y 19. And then the other way we could write this problem if we wanted to would be negative 12i plus 19j. And that gives us our direction. All right. So that is our very first example for vectors. And let's go into, and when you guys get to multivariable, they're going to explain this a lot better than what I'm doing right here about how to find the magnitude and all this stuff right here. I'm just really showing you guys the simplistic way of doing these problems. So anyways, question number 2 says the vector v has a length of 3 and makes an angle of 30 degrees, which is pi over 6 with the positive x-axis. So for this problem, we're going to go ahead and do positive x-axis, which is right here. And then it's going to say that the vector is going to make a pi over 6 degrees. So pi over 6 degrees. Sorry, pi over 6 radian. I don't know why I'm saying degrees. Sorry, pi over 6 radian, or 30 degrees, along the x-axis. And it tells us that this vector, so I'm going to go ahead and make this pink. So our vector v is going to be this right here. This is it. And so this distance between here and here, this is going to end up being 3. This is going to end up being 3. And so we want to write v as a linear combination of I and j. Well, again, I and j is kind of intertwined with x and y, so I is going to be in this direction, and then j is going to be in this direction. So essentially, guys, what do you have here? You have a special right triangle. Well, you have a right triangle that has, you're given one side, and you're also given the angle. So if I wanted to find j, I could simply say that the sine of pi over 6 is equal to the distance j all over 3. Okay? So then I would multiply, or I'd cross multiply 3, and I get sine of pi over 6 is 1/2. So I get 3 times 1/2 is equal to j. So our number right here in front of the j would be 3 over 2. 3 over 2. And then, similarly, if we want to find what I is, well, we can find the cosine of pi over 6. Then we get that that's going to be equal to the adjacent side, or the hypotenuse. And so just like the previous one, we can multiply by 3, and then we get the cosine of pi over 6, which is the square root of 3 over 2, times 3. And so I can go ahead and say that this ends up being equal to, let's continue to color here, equal to 3 square roots of 3 over 2i plus 3/2 j. And that is all you can do. And if we wanted to, we could rewrite this as 3 square roots of 3 over 2 and then 3, 2. And again, that gives us our, what we're doing the transformation for it. The translation, actually, I should say. So there you go for that. We're going to keep on going with this video. So let's go ahead and look at more stuff. The bottom here is going to give us some vector things, and it's talking to us about the limit. If I look at the limit, if I give you the vector r, and it gives us in terms of a function f with I and a function g of j, then it's basically saying that if the limit as t approaches a of r is equal to this limit as t approaches a of f of t plus the limit as t approaches a of g of t. So that's what we're saying with this. That if these are equal to each other, then the limits are also going to be equal to each other. And the reason that you get this, and this is very similar to the definition of continuity, right? If the functions are equal to each other, then I can say that their limits have to also be equal to each other. And that goes through the definition of continuity. So let's look at the next example. So here we go with this one, and all we're doing here, ladies and gentlemen, is breaking this up. So it says find the limit as t approaches pi over 3. And then we can do these individually. So let's do that. And that's kind of what the theorem said at the very beginning. Just like this. And just like any good limit, you substitute in. All right, you're really good at substituting in here. So we're going to have pi over 3. And then we're going to do pi over 3 squared. So we're going to end up getting that this is going to be pi squared over 9. And then we're going to do our I. And then we're going to go ahead and plug in, substitute pi over 3 to sine, and we're going to get sine of pi over 3. Sine of pi over 3 is going to be the square root of 3 over 2, j. And that is all that you do for these problems. So here, you're really just looking at the functions themselves when you're taking the limit, and you're evaluating this limit of these functions. Substitution's a really awesome way for this to solve them. Sometimes, though, if substitution doesn't work, then you can use any of your other techniques that you guys learn with limits to be able to solve them. So the last example we're going to do in this video is find the intervals on which this f of t is equal to 1 over t I plus t squared j is continuous. And so all you're looking for here, and this was also talked about at the beginning of our notes, where we're looking at domain. So the function 1 over t is actually continuous on every variable for t except for where t is equal to 0. And then t squared is continuous for all real numbers. So therefore, the intervals for which this function is continuous is only dependent on the domain of these individual functions themselves. So it's going to be from negative infinity to 0, and then 0 to positive infinity. So you're just looking at where the functions are discontinuous. So that's where I'm going to end that video, ladies and gentlemen. I'll see you guys in the next one when we start talking about derivatives of our vectors. So I'll see you guys soon.